All right, let's talk about something that sounds, well, completely made up. Imaginary numbers. But what if I told you that these imaginary things are actually the secret code behind pretty much everything in our reality? Yeah, stick with me. We're going to unlock a whole new way of looking at the world.
So, let's kick things off with a little puzzle. A math problem that seems to break all the rules. Look at this. X squared plus 1 equals 0. Now, you might be thinking, okay, I can solve that, but can you? Think about it. What number, when you multiply it by itself, gives you -1, right? It just doesn't work. Any number you can think of, positive or negative, when you square it, it becomes positive. So this equation, it looks totally impossible.
Okay, so here's the game plan. We're going to look at why our regular numbers just aren't cutting it. Then, we'll meet the hero of our story, the imaginary number I. We'll figure out how to actually use these things, learn a neat little trick for dividing them, and then, the best part, we'll see how they're secretly running the show in the real world.
All right. First up, a problem in plain sight. This is all about when our good old real numbers just aren't enough to get the job done.
So here's the heart of the problem, right? You take any real number, any number at all, and you square it. What happens? A positive times a positive, that's positive. And a negative times a negative, well, that's also positive. There's no way to get to -1. It's like a brick wall. It tells us that the numbers we're used to, well, they're missing something. So, what do you do when you hit a wall like that? You get creative. This brings us to our next section, the imaginary solution, I. Basically, we had to invent a whole new number. And this is the big idea. It's so simple, it's brilliant. Mathematicians just said, you know what? Let's just create a number that does what we want. Let's define a new number I to be the square root of -1. So by its very definition, I squared is -1. And just like that, boom, our impossible equation, it's solved, x equals I. Okay, so now that we have I, we can open up this whole new dimension of numbers, literally. We get what's called a complex number. It's got two parts, a real part A, an imaginary part bi. I love the map analogy for this. The real part A is your east-west coordinate. The imaginary part bi is your north-south. It gives numbers a whole new direction to move in.
Now here's where things get really, really cool. If you start taking I to different powers, you find this incredible pattern. I to the first power is just I. I squared, we already know that's -1. I cubed is -I. And I to the fourth, it's 1. And then it just repeats forever, this beautiful four-step cycle. And trust me, that repeating pattern is a huge deal. Okay, so we've got these new numbers. How do we actually, do math with them? Let's get into working with complex numbers. And don't worry, the rules are actually pretty intuitive. Adding and subtracting? Piece of cake, honestly. You just combine the like terms. So you add the real parts together, and you add the imaginary parts together. That's it. It's exactly like sorting things. Apples with apples, oranges with oranges. Real parts stick together, imaginary parts stick together. Simple as that. All right, moving on. We need to talk about the conjugate secret trick. This is all about how to handle division, because you can't just divide by I in the usual way. So here's the snag. In math, it's kind of a big no-no to leave an imaginary number in the bottom of a fraction, in the denominator. It's just not clean. We need some kind of trick to make that denominator a nice, normal, real number again.
And that trick? It has a name, the complex conjugate. This is our secret weapon, and it's so easy. All you do is take the complex number and just flip the sign in the middle, the sign on the imaginary part. So the conjugate of a plus bi is just a minus bi. It's like its perfect opposite. It's mirror image. Okay, so here's how you use it. Let's say you're dividing 10 plus 5i by 4 minus 3i. First, you find the conjugate of the bottom part. The conjugate of 4 minus 3i is 4 plus 3i. Easy. Then, you multiply the entire fraction, top and bottom, by that conjugate. And when you do the math, something awesome happens. The imaginary parts in the denominator completely cancel out, every single time. It's designed to do that. You're left with a nice real number on the bottom, and in this case, the whole thing simplifies to 1 plus 2i. Okay, we've done a lot of theory, but I know what you're thinking. Why does any of this matter? This is where it all comes together. Let's talk about real numbers and some very real applications.
The name imaginary number might be the worst branding in the history of mathematics. Seriously. Because these numbers, they are the hidden language behind our physical reality. They are absolutely crucial for describing anything, and I mean anything that pulses or rotates or moves in a wave.
Think about it. Electrical engineering and our power grids, that's all complex numbers. Signal processing, the Wi-Fi, your phone signal, couldn't exist without them. Quantum mechanics, the very fabric of reality, yep, you guessed it, complex numbers. Even control theory, medical imaging like MRIs and 3D graphics, they were all powered by this imaginary math.
Here's a perfect example you might be using right now. Noise-canceling headphones. How do they work? Well, they analyze the sound wave of the noise around you using complex numbers. Then, they create the exact opposite wave and play it back. The two waves cancel each other out, and you get silence. That's literally complex math happening inside your headphones. How cool is that?
So, what does this all mean? It means these so-called imaginary numbers don't just solve equations, they actually describe reality. It just goes to show you, sometimes, to understand the real world, you have to be willing to imagine something brand new. Which really makes you wonder, right? What else are we missing? Just because we haven't imagined the right tool to see it yet.